Let's now talk about another state function called enthalpy. Having gone through the last few videos in the previous section, we've discussed in great detail that delta E is always going to be the constant volume heat, regardless of whether a process actually occurs at constant volume or not. The problem is that the vast majority of things that we do as chemists do not occur at constant volume, but rather the vast majority of chemical reactions we do in a lab are done at a constant pressure. And so if you're measuring the heat flow for a reaction that you do in a lab, you're not measuring the constant volume heat. You're not measuring delta E. You're measuring the constant pressure heat. So we need another state function that describes what constant pressure heat is. And that's where enthalpy comes in. Enthalpy will tell us what the constant pressure heat is for a process. What we're going to do is define a new state function called enthalpy, and we use the letter capital H to represent that. And the definition is enthalpy is equal to internal energy plus the product of pressure and volume. Another way of saying that is that the enthalpy that a system has is equal to the internal energy of the system plus this extra factor of PV. Now, we have to think about what that factor of PV could mean. Pressure times volume gives you units of energy. And if you have a system that occupies a certain volume at a given pressure, there is some energy associated with that space that the system is taking up. And so what enthalpy is telling you is what the internal energy of the system is, plus the energy that it takes to confine the system to a given volume at a certain pressure. That's what that PV factor means. Now, we're not interested in knowing what the absolute enthalpy is for a system. When we're doing thermodynamics and when we're doing chemistry, we're interested in studying changes. And so what we can do is take the delta of both sides of the equation to say that the change in enthalpy is equal to delta E plus delta, the product of pressure and volume. Now, this is just the definition of enthalpy. This is how we've chosen to define this state function. Now, because of the way that we have chosen to define enthalpy, it turns out that the change in enthalpy will be equal to the heat at a constant pressure. And I'm not going to go through the whole proof here in this video, but if you want to see it, it's in the textbook in section 9.2. The main takeaway message is that enthalpy is the heat at a constant pressure. And because enthalpy is a state function, the change in enthalpy will always be equal to the constant pressure heat, regardless of whether a process actually occurs at constant pressure or not. It doesn't matter what the pathway is. It doesn't matter if it's a constant pressure pathway or a constant volume pathway. The change in enthalpy will always be equal to the constant pressure heat, no matter what. At this point, I think it's a good idea to take a look at a summary of all the equations that we've seen so far. So we'll first start off by looking at a couple of equations that are always true up here at the top of the slide. And the first law of thermodynamics, delta E equals Q plus W, is an equation that is always true for any process that would involve gases or solids or liquids or phase changes or chemical reactions. Delta E equals Q plus W is always true. It's a law. It's the first law of thermodynamics. Additionally, the equation delta H equals delta E plus delta PV is always true because that is a definition. So that will be true for ideal gases or solids or liquids or phase changes or chemical reactions. Then there are some additional equations that we've seen that hold true, but only for ideal gas processes. This would be this whole suite of equations that we've seen that allows us to calculate Q, W, delta E, and delta H. And I broke it down to each of these variables and the equation that you would use for different types of pathways. What we see is that for path-dependent variables like Q and W, the equations that you use differ depending on whether you're using a constant pressure or a constant volume pathway, right? For Q, at constant pressure, you do NCP delta T, and at constant volume, you do NCV delta T. For work, at constant pressure, it's negative P external delta V, and at constant volume, work is 0, right? So different things for the different paths. But for the state functions, delta E and delta H, the equations are path independent. It doesn't matter which pathway you use. For delta E, we will always use NCV delta T because delta E is always the constant volume heat. I will refer you back to the previous video where we went through a numerical exercise as well as an algebraic exercise to illustrate this, we calculated delta E on both a constant pressure and constant volume pathway and found that in both cases, delta E was equal to NCV delta T. For delta H, that's always the constant pressure heat, and so regardless of whether the process occurs on a constant pressure or constant volume pathway, delta H is NCP delta T, no matter what. It's helpful, I think, to see all of these equations organized because knowing which equation to use and at what time is crucial when you're doing thermodynamics. Now let's get practice with another pathway problem. Here in this problem, we're told we have a 1 mole sample of helium gas heated from 298 Kelvin to 350 Kelvin at a constant pressure of 1 atmosphere. And we're asked to calculate all 4 thermodynamic variables that we've been studying so far: W, Q, delta E, and delta H. Now, in solving this problem, it's so important that you make sure that you're using the right equations and at the right time. And there are some tricks that you can use to make solving this problem really quick. And there are some methods that you could use to solve the problem that would take a really long time. So let's talk about the quickest and most efficient way to get to the answer on this problem. I'm going to start by calculating the state functions because there's only one equation that we can use for each of our state functions. We know exactly what we're going to use for delta H. We know that delta H is always going to be NCP delta T for an ideal gas. Then we have that delta H is equal to N, which is 1 mole, and then we have to think about what CP is. So helium, right, is a monatomic ideal gas. So we know information about the values of CV and CP for a monatomic ideal gas. We know that CV is equal to 3/2 R, and we know that CP is equal to 5/2 R. We talked about that previously in the chapter. So with that in mind, we can plug in CP is 5/2 times R, 8.314 joules per mole per Kelvin. Then delta T is always T final minus T initial. So T final of 350 Kelvin minus T initial of 298 Kelvin. In terms of the units, the moles cancel out, the kelvins cancel out, and I'm left with just units of joules. And the value of delta H is 1081 joules. All right, so there's that one. Next, we can look at delta E. Delta E, as discussed in great detail over the first part of this presentation as well as the last video, delta E, no matter what the pathway is NCV delta T. It's always the constant volume heat, even if it doesn't occur at constant volume. So delta E is 1 mole times CV for a monatomic ideal gas is 3/2 R. So 3/2 times 8.314. Delta T, T final of 350 minus T initial of 298. In terms of the units, again, the moles and the Kelvin cancel out, and I'm left with just units of joules, and the value that I get for delta E is 648 joules. All right, so I've taken care of my state functions. Now I'm going to go on to the next slide and worry about the path-dependent variables. For Q, at constant pressure, we can say that Q equals NCP delta T. And we already calculated that, right? We already found that when we got delta H. We found that NCP delta T was equal to 1081 joules. That was on the last slide when we found delta H. So that one is already done. When pressure is constant, Q and delta H will be the same. Lastly, for the work, there are a couple of options that you have in calculating work. One way is you can do work equals negative P external times delta V, and then you'd have to use the ideal gas law to find what V final and V initial are, and then you'd plug that into the work equation. You'd have to convert the units to turn liters atmospheres into joules, and it takes a lot of time, and it's a real mess. But there's a shortcut that you can use because of the way that we've worked through this problem. So the shorter way is to recognize that we know what delta E and Q are. And delta E, Q, and W are all related using the first law. So we're going to use the first law of thermodynamics. Delta E equals Q plus W. And so to solve this for work, we could do W equals delta E minus Q. We know what both of these numbers are. We know that delta E is 648 joules, minus Q is 1081 joules. And so when you plug that into your calculator, you get work is equal to negative 433 joules. You don't have to bother with using the ideal gas law or doing anything like that. This is a shorter way of solving the problem that allows you to save a lot of time because you know about state functions and you know what equations to use and at what time. This is a big time saver. I highly recommend reworking this problem again on your own so you can get comfortable with the equations. And I also really recommend taking a look at example problem 9.2 in the textbook, because in this example problem, what you're going to do is take a look at a pathway problem that has 4 parts, and you're going to calculate Q, W, delta H, and delta E along each of these 4 parts. And so that's going to allow you to get practice with doing 16 calculations like this. So you really will get comfortable with using these equations. Next up, we're going to talk about enthalpy changes for chemical reactions and phase changes.